All right, and we're going to continue on here. We're talking about earthquake waves. I'm talking about how they go through the earth as they hit the different curved surfaces inside. They refract or bend, we said, just like light going through a lens, and so they refract and bend, and their speed changes if they change from one kind to another. All right, and we said a lot of these stations were originally set up to monitor nuclear testing, but later they became useful for study of earthquakes. All right, and one of the first things they noticed is that at a certain distance underneath the Earth, the S waves disappeared. Okay, so S waves, secondary waves that are the slower ones that cannot go through liquid, would disappear. And when you have these different stations over here along the Earth, okay, say this is our epicenter. That's where the earthquake actually occurs, right there. Okay, usually down below the surface a little bit, not actually up on top of the surface. Okay, that's the epicenter. Well, all right. And it sends out these waves. Well, they would keep receiving them until they got to about 105 degrees away, and on either side or all the way around the Earth. This would be three-dimensional sticking out. And all of a sudden, the S waves disappeared. And based on where they disappeared and the angle, the best explanation was that they were hitting something liquid because they cannot go through liquid. But the P waves continue to pass on through. And so, well, if the P waves are passing through, then it must be because it's a liquid. They can go through a liquid, but the others could not. Okay, and so, but the P waves didn't behave quite normally. There's still a little bit of a shadow wave. I mean, from the S waves are all the way from here to here. They're completely blocked out. So they must be. We thought it must be a liquid, but the P waves are still getting through, but they're not hitting, they're still not coming in the same pattern that they were before, where we'd expect to find P waves all along the way. They changed their pattern. Okay, and so the P waves act as though they were bending and then bending again, and when they did this little double bend here, they curve this way and then they curve back this way, they were hitting down here instead. And so there was a little shadow of the P waves between about 140 degrees from the epicenter all the way around the Earth. There was this shadow zone where there's no P waves either. And they figured, well, that must be because it's hitting this liquid area, it's curving and bouncing. Now, but then they got a little more complicated over here, and they didn't get the pattern of P waves they would expect. And because of that, they're assuming that it must be hitting something solid in here that was causing it to refract again. So you're going from a liquid to a solid, and so it was making them bend again. And when they allowed for that, that explained where the P waves were showing up down here on the other side. All right. So basically, the S waves disappearing told us there must be a liquid layer here, and based on the speed of the P waves, which at least slowed down when they hit that area, we figured that would make sense because they would slow down in the liquid. All right, and so that told us that there must be a liquid layer in there, but also they seem to be refracting again based on the pattern of where they showed up on the surface, and so we assumed that meant there must be another layer in here that was causing them to bend again. And to explain that, they also seem to speed up a little bit, so they're coming out faster than we would have expected them to. So we figured they must have gone through a solid inner core, and so that's why we think the outer core is more liquidy, the inner core is more solid. Also, another pattern was a man named Andreeva or something like that, Mohorovsivik or something like that. Okay, he was a Russian, and it's still not quite spelled right. Mohorovsivik, B-I-C-I-C, but yeah. And he noticed that as these waves were going into the surface, somewhere in here, in this top part, they tended to speed up and go faster. Okay, and so he was trying to explain that, and his hypothesis was that once you got to a certain depth down here, the rocks became denser, and because they're denser, like we said before, if they're denser and elastic, it will start speeding up faster. And so it seemed that his data seemed to suggest that this happened all the way around the Earth. And so this break here is called the Moho discontinuity. In other words, there's something's not, this is not continuity. There we go. Let me get that spelled right. Discontinuity. And the idea is that something's happening here and it's not continuous. It's not just acting the same. Something changes here. And so that's called the moho, which is better than morphoviscic discontinuity. Okay? And that just means it got denser here. And so what we've said, these are the lighter, less dense rocks above that it was going fairly slow through. We call it the crust. And this faster, where it speeds up in here, is called the mantle. And this is basically where we have our different layers. Then we have the crust, then we have the mantle, then we have the outer core, and then we have the inner core on the inside. And this is what we think now are the major layers of the Earth. We have a less dense layer in crust, then we have a denser mantle, then we have a liquid outer core here, and then we have a solid inner core on the inside. So let's just look at these different layers with a little more specific. It's not going to get real detailed, but let's start with the core. Okay, the core is mostly made of heavier metals, we think, like iron and nickel, predominantly. Okay, part of this has to do based on the density and so forth. Now, the inner core then is the very hottest temperatures, we think. Okay, as you go down, as you get deeper in here, the temperatures get hotter and hotter and hotter. Okay, and someone says, well, if it gets hotter and hotter, then you would expect it to melt down here. Well, the thing is, at the center of the Earth down here, the pressure is so high that it actually keeps it a solid, and that's what we think. Is being in the absolute center of the Earth, the gravitational forces and the pressure of all the rock layers above it is so high that it keeps it a solid. Even though it's very, very hot, much hotter than these other layers, it's still going to become a solid because of the extent pressure. It's kind of like a pressure cooker. You take a pressure cooker, put the lid on it, and you bolt it shut. Because it keeps high pressure in there, the water that you're using to cook things will stay water. Yes, there'll be steam filling this area, but after a point, there's so much pressure, there's nowhere for the gases to escape and take up more places, and so instead you have a this pressure cooker type thing where it stays water, but you can have it at a lot higher temperatures. If you took the lid off, then all this water would turn into steam. Okay, but you can get it to much higher temperatures. If you're boiling water, you can only heat it at 100 degrees. That's it. But if you put it in a pressure cooker, you can get up to a lot higher temperatures, and it will remain a liquid and still cook things. Okay, and that's kind of how pressure cookers work. But since they are under pressure, if it blows the lid off, then you've got some serious problems there because you've got hot steam and water going everywhere, and they're very, very high pressure. All right, then you have the outer core. Okay, and in the outer core, it's not as hot as it was, but there's less pressure too, and that's why we think this is the molten area. This is liquidy, okay, based on the S waves not passing through it and so forth. Because even though it's still hot, it's still very hot, and there's less pressure. So because of the less pressure, it is allowed to change into a liquid. All right, now this means that it can flow. All right, and as this outer core flows, we think this flow is kind of important. Now, when we say flow, we're not talking like a river. We're talking about a flow rate of maybe a few kilometers, 3 or 4 miles a year. Okay, so we're talking a very, very slow flowing stuff. But as it moves inside the Earth here, here's the inner core, and as this flows around it, the motion of that produces a magnetic field. Okay, well, first of all, it produces a flowing electric current, and that current produces a magnetic field around the whole Earth. And so when we talk about the Earth's magnetic field, the North Pole being magnetic north, or near magnetic north, okay, then that's what produces it. We think that the flow of the inner core, all right, produces electricity, or electric charges, or current, all right, and that current causes the magnetic field. Okay, if you took the physics part, we talked a little bit about how electricity and magnets are related to each other. Currents can create magnetic fields, and magnetic fields can create electricity. That's how power plants work and generators. But basically, this is the Earth's magnetic field. Now, we think that there's evidence that based on rocks that solidified at different times. The iron and magnetic elements in them are lined up in different directions. So we think in the past this rate of flow and the direction of flow may have changed at different times, and that's changed the Earth's magnetic field. So it hasn't necessarily, north hasn't always been north. Okay, and so as this flow changes and the direction of it changes, it could change where magnetic north is. And over time we think that has happened. All right, we'll talk more about that in later chapters, but that's something we think may have changed in the past. So next, as we're moving out from the center of the Earth, we have the inner core, the outer core. Then we have the mantle. Okay, and the mantle is the thickest layer of the Earth. Okay, the biggest part of the Earth, if you were to weigh it and so forth, the thickest and the biggest part of it. 84% of it by volume, basically. Okay, so we're talking almost all of it, all but 1/5 of it, more than 4/5 of it, by volume, is mantle. Okay, so this is the thickest layer. It's about 2,900 kilometers. Divide that roughly in two, so about 1,400 miles. Okay, 1,400 miles, give or take a little bit. Okay, so about that. So this is a very thick layer, and it takes up a lot part of what we know of the Earth. Okay, now it's mostly made, we talked about iron and nickel primarily, and the core down here is mostly iron and nickel. In this case, we're talking about, they still have a lot of iron, so we say they're iron rich, but they are more silicate rocks, which if you remember, silicate is going to be silicon and oxygen. So these are a little bit different kind of composition than the others, not nearly as dense as those before. Now, it's separated in two parts. As you can see over here, we have the lower mantle and we have the upper mantle. All right, so let's talk about the lower mantle first. The lower mantle, okay, is closer to the center. All right, and it is completely solid. All right, because of, we think, the pressure. The pressure is great enough that for these rocks, the material they're made out of, being iron-rich silicate instead of iron and nickel, it just becomes solid. Okay, and so it's just a solid, doesn't move, doesn't do anything like that. Like I said, there's a constant play going on between pressure and heat, and in this case, the pressure wins and it keeps it as a solid. All right. Now the upper mantle is part that we're probably a little more interested in because it's getting closer to where we live. All right, and it has two parts. All right, the top part of the upper mantle is called the asthenosphere. asthenosphere, asthenosphere, not Athensosphere, but asthenosphere. Okay, and the asthenosphere has plasticity. Okay, plasticity. Someone said, well, what is plasticity? It's made out of plastic? No. Okay, it's made out of iron, silicate minerals. We know that. But basically, it means it can kind of move. Okay, it can flow without actually melting. All right, and so I said, well, how can you flow without melting? And that's kind of hard for us to understand because at our temperatures and pressures, we don't see that much. But we're talking about kind of different stuff than what we're used to at the surface here because you have such high pressures, and so things behave a little different. And so even though it doesn't actually melt, it does move slowly. Okay, and so it can flow and but it doesn't really melt and turn into a liquid. Okay, and because of this has slow-moving convection currents. Currents, kind of like we could find in water. In this picture here, we talk about if you heat up water, we've all seen this, boiling water, and it goes in this convection current where it heats up, rises, sinks down, and comes back down, and just keeps going around and around and around, okay, all the way throughout the pan. And the same thing can happen in the Earth. Here's the crust up here, okay, and the asthenosphere, we think, since it flows, but very slowly, because it's not really liquid, but it rises and it comes back down, and we have these different convection currents that flow in this area, and we'll talk a lot more about that in the next chapter. But basically, we think to go all the way around here would take about 100 million years. So it's obviously not something that's happening very quickly. Okay. All right, and so that's what we think is happening in the asthenosphere, which is the lower part. I may have said that wrong earlier, but it's lower part of the mantle.